Black holes are the universe's cleanest horror story, objects so dense that light, the fastest thing we know, bends, stalls, and never climbs back out, get close enough and a planet, a star, even a phone you throw for science fiction comedy all share the same fate, past a one-way border. You stay inside, hidden from the rest of the cosmos forever. But the stars of this video are not the famous monster, they are their missing siblings. White holes. James Webb did not invent that twin. It made the twin impossible to ignore. Night after night, Webb keeps finding black holes that look too massive, too soon. Engines already roaring when the universe was only a few 100 million years old. Every sharper picture of what a black hole is allowed to be also sharpens the cage around what a black hole is not. And sitting in that cage, in Einstein's equations, is an object that does the opposite of everything Webb is photographing: white hole. The story behind both siblings begins in the 20th century, when a then unknown young physicist published a paper so disruptive that physics is still digesting it. That physicist was Albert Einstein, and the paper introduced special relativity. For this story, the key gift of special relativity is simple and brutal. Time is not absolute, it depends on how fast you move. The faster you travel relative to someone standing still, the slower your clock runs for them. Clocks are not universal metronomes, they are local instruments glued to motion. Then 1915 made the hole deeper. Einstein published general relativity. Space and time were no longer a fixed stage, they were a fabric that mass and energy could bend. And that bending is what we feel as gravity. Newton's force became geometry. Beautiful, terrifying, incomplete in a specific way. The new equations needed solutions, and one of the first questions was how a round, massive object, a star, a planet, would dent that fabric. Less than a year later, Carl Schwarzschild found solutions while serving far from any ivory tower. None of them was ugly enough that both Schwarzschild and Einstein found it unpleasant. It contained a singularity, a point where the math screams that density and curvature go wild. Around that point sits a surface we now call an event horizon, a one-way membrane in space-time. Cross it outward to inward, and the outside universe loses you. You already know where popular culture takes that sentence. Black hole. An object that warps space-time so hard light cannot escape. Detected for real only decades later. First as dynamical monsters in X-ray binaries and galactic centers, later as a shadow photographed by the Event Horizon Telescope, and now as feeding engines, Webb keeps catching in infrared light across the early cosmos. Except that is not where this video is going. Told you the black hole origin story, and the Webb crisis that made black holes feel urgent again. To introduce an object that shares the same mathematical bloodline and then got almost forgotten. White holes. If black holes are the famous siblings who stole every headline, white holes are the ones physics left in a drawer. Many researchers treat them as near twins. Both can have mass, both can spin, both can carry charge. The CARE family of solutions that describes rotating black holes has white hole cousins in the extended diagrams. The difference is the traffic rule painted on the horizon. Black hole pulls matter in, nothing gets out. Not even light. White hole ejects matter. Nothing gets in. Not even light. Its interior is sealed from the outside universe. In the opposite direction, you can, in principle, fall into a black hole. What remains of you will not enjoy the trip. Tides stretch, horizons erase your future options, but the door opens inward. White hole offers no door at all. You cannot enter, neither can I, neither can a photon. Stand outside and you watch an engine that only exhales. The cleanest description accepted in a lot of theoretical talk is this: a white hole is a black hole run backward in time. Film a black hole swallowing gas, the kind of feeding flare Webb's infrared eyes are built to catch. Reverse the film. Now the object is vomiting matter into space. That reversed movie is a white hole. Time reversal symmetry loves that move. Thermodynamics hates it. Hold both feelings at once. That tension is the point. It raises an awkward question. If a white hole is spitting matter, where did that matter come from? One idea stitches the siblings into a wormhole. A black hole as entrance in one region of spacetime, a white hole as exit in another, maybe elsewhere in our universe, maybe somewhere stranger. The mathematics of certain wormhole metrics allows a white hole end on one side, a black hole drinks the cosmos on the other. A white hole exhales what was swallowed. Science fiction sold that tunnel as a subway. Real relativity treats most wormholes as unstable, hungry for exotic conditions, and unfriendly to travelers. Still, as a map of the equations, the black-to-white bridge is a legitimate shape on paper. The picture has even been offered as a way to ease the information paradox. Here is the paradox in plain language. General relativity suggests a black hole can swallow information. The detailed arrangement of whatever fell in. Quantum effects say black holes evaporate through Hawking radiation, leaking energy until nothing remains. If they vanish without returning what they ate, quantum mechanics is furious because information is not supposed to be destroyed. Decades of arguments later, the field still fights over how the books balance. One speculative escape hatch. The black hole dumps the information out through a white hole exit somewhere else. Relativity and quantum theory both get to keep their pride. Whether nature uses that hatch is another question entirely, and a fair number of researchers prefer other resolutions that never invoke white holes at all. Loop quantum gravity offers a different story. In some versions, space-time itself comes in discrete chunks. Imagine a quilt of tiny cells, each with a quantum state. When a black hole evaporates and shrinks toward the size of those cells, the remnant might rebound as a white hole. The singularity softens into a bounce. Important honesty. That is a hypothesis. Loop quantum gravity is not confirmed. String theory and other approaches compete with different pictures of the deep microstructure. White holes ride on those debates. They do not settle them. Treating a white hole as a quantum rebound is a research program, not a museum label, and not something Webb can stamp with a confirmation label tonight. Here is a deeper problem. Maybe the deepest for existence claim. General relativity allows white hole solutions on paper. It does not hand you a clean formation recipe, the way stellar collapse hands you a black hole. Massive stars that burn out can crush into black holes. Supermassive black holes can grow by feeding and merging until they sit in galactic hearts like quiet tyrants. The same engines Webb keeps finding too early, too heavy, too loud. The same equations do not give white holes an equally natural birth channel in our messy universe. Even if a white hole appeared, the math suggests it would be fragile. It wants a perfect vacuum. No particle colliding with matter flung from its horizon could tip the whole thing into collapsing into a black hole again. Instant drama. Instant death of the white hole. An object that can only live in an empty room is a poor candidate for a universe full of dust, gas, and light. The same dusty, glowing universe Webb was built to read. So why study them? Because the same metrics that describe white holes give theorists a playground for other singularities, including the one that began our expanding universe. A white hole contains a singularity that ejects matter. The Big Bang, in cartoon form, is a singularity that ejects everything we'll call the cosmos. That rhyme does not prove the Big Bang was a white hole. Pattern-hungry brains love that leap. Some researchers explore cosmological models with white hole-like features anyway. The useful version is milder. Studying white hole mathematics may sharpen how we talk about a past singularity we cannot visit, a region where classical geometry breaks and quantum gravity must take over. Webb cannot photograph the first instant. It can photograph the aftermath, the earliest black holes, the earliest galaxies, and force the theory to confess what those aftermaths still allow. The coincidences keep going when you stare at causal structure. Inside a black hole, the math flips the roles of space and time in a way that makes the singularity a point in your future, unavoidable if you fall in. Your personal timeline ends at that crush. The way every road might lead to a cliff, white hole puts its singularity in the past. Nothing enters a white hole. Just as you cannot stroll into yesterday, the forbidden region is behind you in time, not ahead. Connect a black hole to a white hole across an extended space-time diagram, and the singularity can sit in both past and future at once. A kind of tunnel that smells like time travel even when nobody is booking tickets. Again, mathematics first, Haurism never. Popular articles that promise white hole time machines are selling the diagram, not a vehicle. Observers have looked for white hole signatures anyway. Sudden explosions, odd radio bursts, events that look like matter appearing from nowhere. Webb's infrared vision is exactly the kind of eye you would want on a transient that dumps energy into the sky and then vanishes. So far, every candidate has better ordinary explanations. Supernovas, magnetars, flares near ordinary black holes, instrumental ghosts. Absence of evidence is not proof of absence, but it is a long silence for an object that should, if bright, announce itself by vomiting energy into the sky, including into the wavelengths Webb was designed to catch, cannot end without the cold water. There is no confirmed observational evidence that white holes exist. There may be solutions that live only on paper, like countless other mathematical ghosts. Yes, black holes once looked like pure math too, and now we have Event Horizon Telescope images of their shadows, gravitational wave chirps from mergers, stellar orbits whipped around the dark heart of the Milky Way, and Webb's growing catalog of early monsters that refuse the slow growth story. That history does not automatically promote white holes to the same status. White hole, defined as a time-reversed black hole, also punches the second law of thermodynamics in the face. That law says, disorder tends to grow. Entropy climbs. A white hole casually reassembling spilled chaos into neat outgoing matter is like spilled water leaping back into the glass by itself. Possible in a reverse film, hostile to everyday thermodynamics. Any serious white hole cosmology has to explain how that conflict is resolved, or admit the object is an idealization, not a neighbor. Still, the universe is under no obligation to match our comfort. White holes remain one of the strangest legal aliens in Einstein's equations, siblings of the objects Webb keeps finding in galactic wreckage and cosmic dawn, cousins of wormholes, candidates in quantum gravity rebirth stories, and metaphors people keep aiming at the Big Bang. Studying them is not superstition. It is stress testing the grammar of spacetime until the grammar confesses what it allows, what it forbids, and what it merely tolerates on a chalkboard. So when someone asks whether white holes are real, answer carefully. Real as a solution, yes. Einstein's equations allow them. Real as a thing you can point James Webb at tonight. Not yet. Not with the confidence we now give to black holes. The honest status is stricter. White holes are a stress test of causality, thermodynamics, and quantum gravity. They force the theory to confess what a horizon can do when time runs the other way. That confession still matters. Every time Webb, LIGO, or the Event Horizon Telescope tightens what black holes are allowed to be, the forbidden twin gets sharper too. Constraints cut both ways. Universe that makes black holes by the billions and lets Webb photograph them when the cosmos was still young may still refuse white holes, or it may hide them in regimes we have not learned to see. Either outcome teaches something. If white holes are impossible, the impossibility itself is a law of nature written in entropy and causality. If they are possible, then somewhere a horizon is exhaling what another horizon once swallowed. And the sky has been keeping that secret from every camera we have built, including the gold mirrors staring into the dark right now. Black holes trap the future. White holes, if they are real, refuse the present. Between those two sentences sits a century of geometry, a drawer of forgotten solutions, and a reminder that the cosmos can invent monsters we have never photographed, and still force us to understand them on paper before Webb, or any telescope after it, ever catches one in the sky. Thank you for watching.